Hello everybody, here we are, week 1 of prep for the IB exam. I'd like to go over number 5 here in our week 1 packet, so let's get started. First what I'm going to do is I'm going to write down the sum and product rule for roots of a polynomial, whether that polynomial is on the complex plane like you'll see here, or if it's on the real plane only, doesn't matter. So the rule for the sum of the roots, and there will be 5 roots, seeing that this is a quintic polynomial, will be the opposite of a sub n minus 1 over a sub n. So a sub n is the coefficient of the leading term. So in this case, that'll be the coefficient of z to the 5th, which is 1. And the coefficient of the next term in descending order, so make sure your polynomial is in descending order, would be 0 z to the 4th. All right, if n equals 5, then n minus 1 would equal 4. Therefore, 0 is the n minus 1th coefficient. All right, so our sum, it looks like, will equal 0. All right, now for the product of the roots, we take negative 1 to the nth, so in this case n will equal 5, times the constant, right, which in this case will be negative 6, over the leading coefficient, which we know is 1. So our product will equal negative 1 to the 5th times negative 6 over 1. So the product of our roots will be negative 1 times negative 6 over 1, which will be 6. Okay, these formulas here can come in handy. You'll see them come in a number of times into play throughout this packet specifically. So be aware of those. Let's keep moving. Okay, 5b. Show that z minus 1 is a factor of p of z. So if z minus 1 is a factor, then that means z equals 1 is a root or a solution or a 0. Those are all synonyms, right? Root, solution, or 0 for the polynomial given. So let me sneak back up here and remind myself what the function was. There we go. So if 1 is a root, then p of 1 should equal 0. So let's plug in 1 everywhere we see a z. So it'd be 1 to the 5th minus 10 times 1 squared. And all this good stuff. Let's confirm it equals 0. So it's 1 minus 10 plus 15 minus 6, which negative 10, oops, I put a 16 there, goofy. Let me change that, get rid of that one. There we go. Okay, so negative 10, negative 6 is negative 16. Positive 15, positive 1 is a positive 16. There you go, it checks out. All right, so that means that z minus 1 is a factor. And it just so happens in this problem that z minus 1 is a factor not once or twice, but 3 times. Okay? The other 2 roots, so these are all real zeros. Right? 1 is a real 0 3 times. Okay? So z equals 1 is a real 0 3 times. That'll show up in our graph here in a couple minutes. That means I'm going to have 2 more zeros. 2 more. And those will either be complex zeros or real zeros, right? Remind yourself, right now, just sit there and say this to yourself. Complex zeros come in conjugate pairs only. They come in pairs. Okay, so check it out. If I had z to the 5th minus 10z squared, I know you're impressed that I'm doing this by memory, although I am home. Oops, I don't need a 0 there. Although I am home alone without my children right now, which is great. Okay, z minus 1 cubed can be expanded to z cubed minus 3z squared plus 3z minus 1. Okay, that can be expanded. And then, of course, this thing here, we can't do much with other than just rewrite. So it says find values for b and for c. Well, I'm going to find c first because the only way, like this is a constant, right? The only way to get a constant is to take -1 times c. So -6 is equal to -1 times c. Therefore, c has to equal 6. So I'm going to go ahead and clean this up, getting rid of, can I make the eraser bigger? Yeah, a little bit bigger. I'm going to plug a 6 in here for c. All right, c equals 6. Go blue. There we go. All right, and now I'm going to solve for b. Now, in order to solve for b, I'm going to do this in yellow. This might be a total failure. I'm going to find a way to build 15z. I hope you can see that at home. It looks okay on my screen. The way I can build a z is either 3z times 6. Okay, so 3z times 6 times 6. Or -1 times bz plus -1 times bz. And now you can see that I'm going to solve for b. That's my only unknown. So on the left side, I get 15z. On the right side, I get 18z minus bz. A couple ways you could go about this. I'm going to do it just by isolation here. You'll see what I mean in a second. Factoring out a z, 18 minus b, z has to equal 15. Therefore, 15 equals 18 minus b. That tells me that b has to equal 3. Okay, so I found c and I found b. In classic IB fashion, I'm just wondering how is that going to go into the next part of the problem. Find the complex, oh nice, find the complex roots. Okay, so I knew that the complex roots, in this case, well, they're telling me there's complex roots. I didn't know that until right now. But if I had x squared plus bz plus c equal to 0, that's the only other place that my complex roots can come from. The other 3 roots were all 1. So I'm going to plug values in for b and for c, which I found above. B was 3, c was 6. I don't think that's factorable, so I'm going to use the quadratic formula. These should all be z's. Goodness, that should be a z. I do have a z there. This should be a z. Okay, let me make those red. It's going to bother some people, including me. All right, so I'm going to use the quadratic formula. -b. Oh, just so happens that they called that b. Cool. Plus or minus square root b squared. Let's do that up here. B squared minus 4ac will equal 3 squared minus 4 times, goodness, 4 times a times c. So b squared minus 4ac will equal 9 minus 24, which will be -15. Yeah, there's my complex roots. All right, I can't divide by I can't take the square root of a negative number, all over 2a. All right, so that's an acceptable way to leave your answer. Although they might ask you in some cases to put it in a plus bi form. So we do this, plus or minus I root 15 over 2, with the 15 being clearly fully reduced. Okay, I think we got a couple more parts to this problem, so hang with me. What's next? Okay, consider this function. Show that the graph of y equals qx is concave up. Well, concavity has to do with the second derivative. So we want q double prime of x to be greater than 0. That'll confirm that it's concave up. So let's do that. Q prime, taking the derivative of the above function, will be 5x to the 4th minus 20x x plus 15. Second derivative, 20x cubed minus 20. Okay, so at x equals 1, let's figure out what the second derivative is at x equals 1. Looks like it'd be 0. So q double prime at 1 would equal 0. Let me do a little sketch here. At 1 is equal to 0. Okay. And to the right of that, so when x is greater than 1, let's factor this second derivative. So I take out a 20, it'd be x cubed minus 1. So if x was greater than 1, this quantity right here would be greater than 1. And therefore, q double prime of x would be greater than 0. Okay, so we know the second derivative would be positive to the right. Therefore, show that the graph, well, I guess we could sketch it, but we're just going to do a sign analysis here. It would be concave up for x greater than 1. Okay, let's finish this one off with the graph, sketching the graph of q of x, showing clearly the intercept point. Okay, so we already know that q of 0, if we were to look back at the function, if I plugged a 0 in for all x's, q of 0 equals negative 6. And I know that the only real root, right, was at 1. We proved that that was true. The sketch of the graph, if this is a calculator allowed question, which I'm guessing based on the concept that's being presented right now, it probably isn't. But I would use my calculator to see a sketch of the graph. But otherwise, honestly, you know, I would just do a general sketch here. I know that the y-intercept is negative 6. I know that the x-intercept is positive 1. And I know it's concave up when x is greater than 1. So I'm going to guess it looks something like that. Ooh, that was not great. Let's do this. All right, that was even worse. Great, cool. I think the spacing, I got issues. But I would assume based on this, and I could check the second derivative to the left, but I'm going to say that there's a point of inflection here. As you can tell, the concavity of the function q changes at that point. So what we'll do here then is, you guys, we'll call this, I guess I have to label these, whatever. So I have a x-intercept here at 1, 0, and a y-intercept here at 0, negative 6. And I believe that's it for problem number 5. Yes, it is. So see me back for the next video, and let me know if you got any questions.